In Book 1 of Euclid's Elements, Euclid describes 5 postulates on which he based his geometry. The first one is a straight line segment can be drawn joining any 2 points. Second, any straight line segment can be extended indefinitely in a straight line. The third one is, given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as center. The fourth is, all right angles are congruent. And then the last one is, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. This postulate show is equivalent to what is known as the parallel postulate. However, conclusions drawn from the postulates are very controversial, for they don't all apply on 3-dimensional or curved geometries, also known as non-Euclidean surfaces, such as conical, spherical, cylindrical, and hyperbolic surfaces. The first of such conclusions is number 1, a line can never intersect itself. In a Euclidean plane, a line never intersects itself. This does not apply to cones, spheres, and cylinders, and cones going in the east-west or diagonal directions. Chris-Riven shape intrinsically, which does in fact intersect herself on cylinders in the east-west direction and spheres in all directions. Lines appear as circles extrinsically and therefore intersect themselves infinitely. This leads to the conclusion that on any given surface, the number 2 conclusion is all lines look the same extrinsically. On a flat surface, all lines appear the same, for they all carry a linear shape. On a cylinder, 3 different line shapes appear extrinsically. Horizontally, a line gains the shape of a circle. Vertically, it carries a regular linear shape. And in any given diagonal direction, a spiral may be formed on a conical surface. 2 distinct line shapes appear extrinsically. Vertically, a parabola is formed, and either horizontally or diagonally, a ribbon shape is formed. The number 3 conclusion is, given a line and a point not on that line, there is exactly one non-intersecting line that can pass through the point. On 2-dimensional surfaces, this is true. There can only be one line that passes through a point that doesn't intersect that line. On a sphere, all lines must intersect each other. While on a hyperbolic surface, there can be infinite lines that do not intersect another line passing through a point. Therefore, the statement is false on these surfaces. The fourth conclusion is that 2 points determine a unique line. However, on cylinders and cones, this is not the case. On a cylinder, 2 points numerous spirals can be drawn, and in some cases, a singular straight line. On a cone, 2 points may determine extrinsically: a parabola and a ribbon or multiple ribbons. The fifth conclusion is that all straight angles are congruent. On the flat plane, this is true. It can measure 180 degrees, yet this is not true on conical and hyperbolic surfaces. On a cone, all lines not going through the point measures 180 degrees. However, a line going through the point will always measure less than that. On hyperbolic surfaces, depending on where a line is drawn, the measure of a straight angle can change, being anywhere from greater than 0 degrees to less than 360 degrees. From all of this, we can gather that self-contained geometries can occur, or not all Euclid's postulate supply specifically curved surfaces. Euclid lived in the Greek city of Alexandria in Egypt around 2,300 years ago. He spent his life studying and teaching geometry. He published in a book called Elements. To this day, it is the foundation for our understanding of geometry and mathematical processes in general. In the early to mid-1800s, new geometries were studied by mathematicians like Gauss, one of the greatest mathematicians of all time, and his colleague Riemann will cover a bit of what they found. To understand the differences between Euclidean geometry and other possibilities, we start with points and connect them with lines. The shortest distance between 2 points is the line with the least curves. In Euclidean geometry, this is a straight line. In this case, the least curvature is no curvature at all. Another name for the shortest line between 2 points is the geodesic. If we draw geodesics that are each perpendicular to a third line, they will be parallel to each other. Will never cross even they are extended to infinity. This is a key characteristic of flat Euclidean space. What we are talking about here is intrinsic characteristics of the geometry. Things like the sum of the angles of a triangle 180 degrees and the circumference of a circle is 2 pi times its radius. We can bend this two-dimensional surface into a third dimension, and it give it back to the look of curved space, but this curvature is extrinsic by nature. The intrinsic curvature is still flat, parallel lines remain parallel, the sum of the angles of a triangle is still 180 degrees, and the circumference of a circle is still 2 pi times its radius. But there are other possibilities. One possibility for a geometry supposes that the parallel geodesic lines are diverging, getting farther apart, as if space were being stretched between the lines, and the farther up the lines you go, the more the space is stretched. The best example of this is the surface of a saddle or a potato chip. Another possibility for a different geometry supposes that the parallel geodesic lines are converging and will eventually meet. It's as if space were being compressed between the lines, and the farther up the lines you go, the more the space is compressed. The best example of this is the surface of a sphere like the Earth itself. Here the curvature is constant throughout the surface. The baseline is the equator, the perpendicular lines are the lines of longitude, and they meet at the North Pole. Here's the best way to find a geodesic between 2 points on a sphere. First, intercept the sphere with a plane that contains the 2 points plus the center of the sphere. The intersection is called a great circle. The segment of the circle that connects the 2 points is the shortest distance between the 2 points. A parallel of latitude line between the 2 points would be longer. This is why planes in the northern hemisphere travel north and then back south to get the destination at the same latitude rather than travel to west or to east, that they have chosen the shortest distance between the 2 points to save on both time and fuel. Some geodesic routes can save up to 1,000 kilometers. Of course, when it comes to a more generalized curved space, the curvature changes from place to place. If we were to put a car on a curved surface like this one and lock its steering wheel to go straight, it would naturally follow the space's geodesic line from its starting point. When it's done, it will have traveled the shortest distance between its starting point and its ending point.